Next speaker is Snehal. Snehal is the CEO of a company called Horizon3. They're one of the leaders in AppSec testing and security use cases in AI. Snehal was the CTO of JSOC, the Joint Special Operations Command Unit. Prior to that, he was SVP at Splunk, and prior to that, CIO at GE Digital. So, Snehal, welcome.
Thanks. All right. So I'm going to build a little bit on what Don had spoken earlier on AI agents and cybersecurity, in particular the use of AI agents for offensive cyber, so building AI hackers. That's something that we focus on and pioneered at Horizon 3 based on my time within the special operations and intelligence community, and then my time at Splunk, kind of bringing those worlds together. So when you think about AI for offensive cyber, there are two architectural paradigms that have started to emerge. One paradigm is iterative trial and error. And here you've got agents that are exploring step by step, like should I run this command? Did it work? Did it not work? Why didn't it work? How do I tweak or iterate on that command in order to achieve an objective? And then you've got this other approach around structured context and precision prompting. And in that other approach, you're using a variety of techniques to conduct reconnaissance of a target network, enumeration of that target network. You're building a knowledge graph that represents the facts of the environment. And then you're using queries of that knowledge graph to do very precise targeted reasoning problems with LLMs. Between those two, we've used both approaches. We ended up focusing on structured context for precision prompting. I'm going to talk about the differences between the two, at least in offensive cyber. So one, when you look at where we settled, kind of reading this, as you want to hack a network, hack Berkeley's environment or whatever, you need to first discover everything that's network reachable. Every host, port, service, credential, password policy, any other sets of things that are relevant to an attacker to achieve a compromise. And we'll end up organizing that data into a knowledge graph that represents the cyber terrain that we've discovered. And from that knowledge graph, we're going to start to find very targeted reasoning problems. One example is high-value targeting. We found a collection of hosts. What business department do those hosts belong to? Well, it's a targeted reasoning problem. You can't regex your way through that one. And what you want to understand is providing as much detail as you can via prompt to an LLM that says, based on discovered applications, credentials that have access to that server, and so on, we believe these services belong to the accounts receivables department. And the more precise you get in high-value targeting, the more accurate you are in compromising that particular host and understanding the business impact. The same for advanced data pilfering. You stumble onto a shared drive with 1 million files within it, you can't regex your way through those files. How do you use targeted reasoning to figure out that these files are actually 3D CAD drawings for Nimitz-class aircraft carriers, which is actually something our product NodeZero stole a couple of weeks ago from a defense industrial base supplier. From there, it's all about the right LLM for the job. Certain LLMs are really good at an advanced data pilfering problem. Other LLMs are good enough for high-value targeting. And you want to be able to have that selection of right prompt for the job, in partially because of managing costs. If you're a startup, scale up, understanding your gross margins and your costs of tokens becomes super important. And this is where we ended up using Bedrock as that model selector from Amazon. So based on the type of problem we want to go reason against, we can figure out which model in that moment is the best model to use for cost and performance, and then get the answer at a cheap price in order to be able to scale this out as a viable business. And for certain classes, Nova is good. For other classes, variations of Cloud are good. And the point is you want architectural flexibility. So a big question in offensive cyber is, can your hacker agent or attacker agent actually solve a meaningful problem? So for academics, a good range to try is GOAD, Game of Active Directory. Game of Active Directory is actually a pretty tricky cyber range to go off and solve algorithmically. One, you've got easy, medium, and hard. So GOAD hard, it's a 5 VM system. Everything in the hard mode is patched. So you're not using pre-2025 CVEs. You don't have legacy protocols you can exploit. It's a legitimately difficult range. And the reason why this is a hard range to solve for algorithms is you've got multi-step, multi-hop exploits. You've got to compromise machine 1 and use information from machine 1 to laterally maneuver to machine 2. Use information from machine 2 to abuse a trust domain into domain 2, and so on and so forth. You also have conditional execution. Based on a certain set of conditions, you can do one type of exploit. If some of those conditions are absent, you've got to try a different technique to get in. You have to discover and abuse trust. And you've got to do this with no prior knowledge of the environment. So there's no cheating, there's no predefined runbooks, there's no pre-known credentials. And you want to do this with no humans in the loop and no humans on the loop. You don't want to have a human nudge it. So it's an incredibly difficult problem for an agent to go solve. And when you think about an expert hacker, if you're OSCP certified with multiple years of experience and you're really good and seasoned, it should take you 12 to 16 hours to fully compromise the GOAD environment, compromising all 5 hosts, all 3 domains. For us, with NodeZero, it took 14 minutes and 25 seconds. That works out to about 50x faster than the best humans or the senior pen testers that are out there. So pretty good. Now that's a range. What does this look like in the real world? We run more pen tests today than consulting firms run a year. We ran more pen tests last year than the entire history of computing. Every one of those pen tests collecting telemetry to improve the underlying algorithms and decision making. And in the defense industrial base, and I'm keynoting Black Hat next week with NSA on this topic, you can look at some of the stats. Fastest to credential compromise was 5.5 minutes. 72 minutes was the median across real customer environments. It took 77 seconds to compromise a domain in the fastest. That means in 77 seconds, we've got keys to the kingdom. We can lock you out, steal your data, destroy your environment. So if your SOC can't detect and respond in 76 seconds, it's game over. This is super important as you build real-world agents. The final bit is when you look at the cost profile. So in structured reasoning, when you execute against an environment, 36,000 commands were executed to compromise at a cost of $3 to $10 when you factor in token costs, AWS costs, and so on. In trial and error, you needed to get through 20 to 80 iterations for each of those 36,000 commands. At 5 to 20,000 tokens per input output, that works out to $2,000 per test. So 700x more expensive if you go down the trial and error route versus the structured reasoning route. So I'll end there. I'm out of time. I hope this is a good sense of practical experiences in AI agents for offensive security and cyber generally. Look forward to the panel.